Hello and welcome back. Now we will continue supplemental lecture 6-3 to get you prepared for lab 6 by discussing integral control and integrated full state estimation and feedback. Note that the systems designed with the controller and observer gains have a significant steady state error. In order to reduce the steady state error, integral control can be added to input to the control system. In order to implement integral control to produce zero steady state error, an additional state, x sub I, must be added to the control system with a gain k sub I. The equations for the modified control system and the block diagram are given below. So note, now we have an input r, we have the integrator 1 over s, which provides x sub I, and the gain k sub I, and that feeds into our u, or our input into the plant, and we have the A, B, and C matrix and the output y and the state variables x fed back through the k found by using the controller gain for state variable feedback. The equations for integral control are x sub I dot equals negative cx plus r, and here I show the matrix where it's integrated with the state variable feedback matrices. And the integral state feedback control is u is equal to negative kx plus k sub I x sub I. And here we have those equations with the state variable feedback as well. And for both of these equations, y is equal to c0x. The steps to implement integral state feedback control is to form the state equations with the integrated integral control, find the characteristic equation for the system in step 1, form the desired characteristic equation based upon the design specifications, and finally, find the controller and integral gains by matching coefficients. In-class activity 4. Design the following state feedback control system to have 10% overshoot and a settling time of 0.5 seconds by selecting the controller gains. What is the steady state error of the design system? Modify the control system to include integral control and produce a zero steady state error. Verify that the steady state error is indeed zero. So I want to show you the results first and then talk about how to do the design. So x dot is equal to 0, 1, negative 3, negative 5x plus 0, 1 u plus y equals 1, 0 x. So here I've plotted the results for the original system, the state feedback system, and the integral control. First, the original system is the blue line. You can see here that it does have a significant steady state error and that the settling time is much larger than 0.5 seconds. So then that very, very small green line is after state variable feedback, where we may now have less than a 10% overshoot and a settling time of 0.5 seconds, but the steady state error is huge. And so finally, the red line. The red line is after we've added in the integral control, and now we do have a settling time of 0.5 seconds, but also just as important, we have a 10% overshoot and we have zero steady state error. So now we're going to walk through the steps in order to implement this design. We will do state variable feedback with no integral control first. So let's find the desired characteristic equation. For 10% overshoot, that yields a constraint of zeta equal to 0.591, which yields a constraint of theta equal to 53.76 degrees. For a settling time of 0.5 seconds, that yields a constraint of sigma d equal to 8. So omega d is equal to 10.915. So our desired poles are negative 8 plus or minus j 10.915. So our desired characteristic equation is delta d of s is equal to s squared plus 16s plus 183. And now we'll find a tilde, which is equal to a minus bk, which equals 0, 1, negative 3, minus K1, negative 5 minus K2. So next we're going to find SI minus A tilde, which is S, negative 1, 3 plus K1, S plus 5 plus K2. Delta of S is equal to the determinant of SI minus A tilde, which equals S squared plus 5 plus K2S plus 3 plus K1. So just as we've done before, we now are going to equate coefficients. So 3 plus K1 is equal to 183. So K1 is equal to 180. And 5 plus K2 is equal to 16. So K2 is equal to 11. So the controller K gain is 180, 11. And now because we want to find the current steady state error, we are going to have to derive the transfer function from the A, B, and C matrices. So X dot is equal to the following A matrix now that we have our controller gains: 0, 1, negative 183, negative 16X plus 0, 1, R, and Y is equal to 1, 0, X. So T of S is equal to C times SI minus A tilde inverse B plus D, but we know there is no D, it's 0. And we get that the transfer function is 1 over S squared plus 16S plus 183, which was the characteristic equation we found before. So our steady state error is 1 minus T of 0, which equals 0.995, which we actually are able to see here on our graph by the fact that the green line was so close to the 0. So now let's do the integral control to see if we can correct this steady state error. So now let's add the integral control. So the first thing we need to note here is that when you add integral control, it adds another pole to the system. And since we already know where we want our desired poles to be, they're the dominant poles, we want to add a third pole that's at least 5 times away so that it does not affect the characteristics of the system. So we're going to put our third pole at negative 40. So our new desired characteristic equation is S plus 40 times S plus 8 plus J 10.915 times S plus 8 minus J 10.915. So the desired characteristic equation is now S cubed plus 56S squared plus 823S plus 7,325. So now let's create the matrix for integral state feedback control. So we're going to have x1 dot, x2 dot, and xi dot. Xi dot is for our integral. That's equal to a minus bk, bk sub I, negative c, 0, times x, plus 001R, which equals 010, negative 3 minus K1, negative 5 minus K2, Ki, negative 100, plus 001R, and Y is equal to C0 x or 100x. So next we find SI minus AI, where this matrix here is AI. So that equals S, -1, 0, 3 plus K1, S plus 5 plus K2, negative Ki. And the last row is 1, 0, S. So now the characteristic equation is the determinant of SI minus AI, which equals S cubed plus 5 plus K2 S squared plus 3 plus K1S plus Ki. And just as we did before, we equate coefficients and we get that Ki is equal to 7,326. K2 is equal to 51, and K1 is equal to 820. So the K matrix is 820, 51, 7,326. We get the transfer function T of S equal to C times SI minus A sub I inverse B, which equals 7,326 over S cubed plus 56S squared plus 823S plus 7,326. So the steady state error is 1 minus T of 0, which is equal to 0, which is what we wanted. So now let's try another example. Design the following control system with state feedback integral control to have a 0 steady state error, zeta equal to 0.707, and a time to peak of 3.14 seconds by selecting the controller gains. X dot is equal to 0, 1, -1, -2x plus 0, 1u, and y is equal to 1, 0x. So as before, let's look at the graph of the results first. So we have an original system that actually does have 0 steady state error, but the time to peak is not 3.14 seconds. And the damping ratio is probably not correct either. So we add the state variable feedback, and we now have the correct time to peak and the correct damping ratio. However, our steady state error has dropped significantly. So we need to add the integral controller back so that now we meet all of the requirements, including 0 steady state error, zeta equal to 0.707, and time to peak of 3.14. And this is shown here with the red line for the integral control. Okay, let's get started. For this problem, we're going to do something a little differently. Instead of doing the state variable feedback first, we're just going to go ahead and do the integral state variable feedback for the system. So first, for zeta equal to 0.707, we get that theta equals 45 degrees. And the time to peak equal pi over omega d means that omega d is equal to 1. So our desired poles are -1 plus or minus j. And just as before, we're going to put a third pole at least 5 times away so that these two are the dominant poles. So the third pole is going to be at -5. So the desired characteristic equation is s plus 5 times s plus 1 plus j times s plus 1 minus j, which equals s cubed plus 7s squared plus 12s plus 10. So now we're going to build our integral state variable feedback matrix, which is x dot and xi dot, equal to a minus bk, bk sub I, negative c0 times x plus 0, 1 r, and y equals c0x. Substituting in our values, we get 0, 1, 0, negative 1 minus k1, negative 2 minus k2, negative k sub I, negative 1, 0, 0, times x, plus 0, 0, 1 r, and y equals 1, 0, 0, x. So now we're going to find Si minus A sub I. Si minus A sub I is equal to S0, 0, 0, S0, 0, 0, S, minus 0, 1, 0, negative 1 minus K1, negative 2 minus K2, negative K sub I, negative 1, 0, 0, which equals S negative 1, 0. Note that there was an error before and that this should have actually been positive Ki and this should have been positive Ki. So the second row of the Si minus Ai matrix should be 1 plus K1, S plus 2 plus K2. And here we have negative Ki and 1, 0, S. So now we take the determinant to find delta of S. So delta of S equals the determinant of Si minus A sub I, which equals S cubed plus K2 plus 2, S squared, plus K1 plus 1, S plus Ki. As we've done before, we equate coefficients and we find here that Ki is equal to 10, K1 plus 1 is equal to 12, so K1 equals 11, and K2 plus 2 equals 7, so K2 equals 5. So the K matrix is 11, 5, 10. So now to compare our transfer functions. For the original system, we have T of S is equal to C times Si minus A inverse times B, which is 1 over S squared plus 2S plus 1, which had a steady state error of 0. Then for the state variable feedback system, which we didn't design here, but I'll give you the answer, T of S is equal to C times Si minus A tilde inverse times B is equal to 1 over S squared plus 2S plus 2. And we get that the steady state error is 1/2. And then finally, for the integral state variable feedback system, we get T of S is equal to C times Si minus A subscript B inverse times B equals 10 over S cubed plus 7S squared plus 12S plus 10, which once again has a steady state error of 0, but now we should also have zeta equal to 0.707 and a time to peak of 3.14 seconds. Whereas this one only had the time to peak of 3.14 seconds and a zeta equal to 0.7707, but the steady state error was not 0. And then here was our original system, which had none of the characteristics. In the prior lectures, we used the separation method to design the state controller and observer gains. These two techniques can be combined to design a compensator for an integrated full state feedback and estimated system. So now we're going to put all the things that we've learned together. Where U is equal to negative Kx hat, x dot is equal to ax minus bkx hat, and x hat dot is equal to a minus lcx hat minus bkx hat plus ly, or the quantity a minus bk minus lcx hat plus lcx, and the error is x minus x hat. So these four matrix equations for the observer estimator state equations and the observer error state equations were created from the prior equations that I just read to you. There are 3 steps for estimated state variable design. The first one is to design the full state feedback control law to place the closed loop poles, as we've done before. Then to design the observer to estimate the states. And finally to connect the observer to the full state feedback law by using u equal negative k x hat. Figure 3 shows the block diagram for the control system with integrated full state feedback and estimation. So this here has everything except the integral control that we just discussed. So notice we once again have the input u, we have the A, B, and C matrices, but we now also have the state variable feedback y tilde and the observer estimate x hat dot and x hat. Now we will start our second to last example in class activity 6. For the following control system, design the integrated full state feedback with observer to place controller poles at -6, -1 plus or minus j, and observer poles at -5 plus or minus j5, -1.414. So as before, the first thing I will do is examine the results. So we have x dot equal to 0, 1, 0, 0, 0, 1, -3, -6, -7x, plus 0, 0, 1 u, and y equals 0, 1, 0 x, which means that the second state is the output of the system. So since we're doing state variable estimation, when we look at the graph here, we have state variable x1 with an initial condition of 0.5, x2 with an initial condition of 0.5, and x3 with an initial condition of 0.5. So the error of the state variable would be the difference between the estimated states and the actual states. And what you should notice here is that very quickly the error dies off to 0, and this is what you would design based upon your desired settling time. So since we are given that our poles are at -1 plus or minus j and -1.414, those are the dominant poles for the controller and the observer. So 4 seconds and 4 over 1.414 would be how quickly the observer and the states get to their final value, and you definitely would want the observer to move faster than the actual state so that your estimate is correct as soon as possible. Okay, we'll do the state variable feedback first. So the characteristic equation is s plus 6 times s plus 1 plus j times s plus 1 minus j, and this is the desired characteristic equation. So delta d of s is equal to s cubed plus 8s squared plus 14s plus 12. A minus bk is equal to 0, 1, 0, 0, 0, 1, -3 minus k1, -6 plus k2, -6 minus k2, and -7 minus k3. Then si minus a tilde is equal to s -1, 0, 0, s -1, 3 plus k1, 6 plus k2, and s plus 7 plus k3. So delta of s is equal to the determinant of si minus a tilde, which equals s cubed plus 7 plus k3, s squared plus 6 plus k2, s plus 3 plus k1. When we equate coefficients, we get that 3 plus k1 has to equal 12, so k1 is equal to 9. 6 plus k2 has to equal 14, so k2 is equal to 8. And 7 plus K3 has to equal 8. So K3 is equal to 1. So our K matrix is 9, 8, 1. So now we design our observer. And recall that the A matrix for the observer is A transpose. So the A matrix is 0, 0, negative 3, 1, 0, negative 6, and 0, 1, negative 7. And the B matrix is 0, 1, 0, and the C matrix is 0, 0, 1. So A naught minus L C naught is equal to 0, 0, negative 3 minus L1, 1, 0, negative 6 minus L2, and 0, 1, negative 7 minus L3. So then SI minus the quantity A naught minus LC naught is equal to S 0, 3 plus L1, negative 1 S 6 plus L2, and 0, 1, 0, negative 1 S plus 7 plus L3. So the characteristic equation is the determinant of SI minus the quantity L naught minus LC naught, which equals S cubed plus 7 plus L3 S squared plus 6 plus L2 S plus 3 plus L1. Now our desired observer characteristic equation is found from the given poles: S plus 5 plus J5, S plus 5 minus J5 times S plus 1.41, which equals S cubed plus 11.414 S squared plus 64.14 S plus 70.7. As before, we are going to equate coefficients. 3 plus L1 equals 70.7, so L1 equals 67.7. 6 plus L2 equals 64.14, so L2 equals 58.14. And 7 plus L3 equals 11.414, so L3 equals 4.414, or the L matrix is 67.7, 58.14, 4.414. Okay, for this last example, I think I want you to practice a little. So I'm going to read the problem statement and give you the final solutions. And your task is to walk through the problems I have already provided and see if you can get these answers. For the following control system, design the integrated full stack feedback with observer to place controller poles at -2, -1 plus or minus J, and observer poles at -10 plus or minus J2, -20. So notice for this one that the dominant pole is -10 plus or minus J2, so it's actually significantly faster than the actual system. And if you look at the graph, you see this. So now we have our state variables, and our error almost goes immediately up to the final value, and that is because all of those values are a multiple of 10 greater than the controller poles for the actual system. So when you solve this one, what you should get is that K is equal to 0, 1, -2, and L is equal to 2076, 499, and 34. I encourage you to try to get those values. Finally, we won't do an example, but I did want you to see what it would look like if we had a fully integrated full order observer state variable feedback system, which means we now have also added back in the integral control to make sure we get zero steady state error. You will do an example of this one in lab. So now notice our system has in the grayed out area down here the observer. We also have the state variable feedback from before, but now the new information is over here where we now have a variable, state variable x sub I and k sub I, where we have the integrator added in so that we could get a zero steady state error. This would be the solution to use instead of using a pre-filter. And this concludes today's lecture on the integration of an observer with state variable feedback, as well as a little bit of talk about how we would do integral control as well. Have a great day.